So I mentioned in passing in another video that if you throw a dart at the real number line, your chance of hitting a rational number is exactly 0. And there's no tricks here. The dart is guaranteed to land on the line. And there are an infinite number of rational numbers on the number line, just waiting to be hit. Rational numbers flooding into every crevice between two other rational numbers. Every possible ratio of one integer to another. So many numbers! But yeah, the dart won't hit any of those. 0%. Really, actually 0. Think about them written out with all their digits. There's some nice simple numbers with a finite number of non-zero digits before it's infinite zeros. Then there's rational numbers with repeating digits. Every rational number has a section that repeats infinitely. Sometimes it's just a repeating 0, and sometimes a single digit, and sometimes many digits. The repeating sections may get longer and further out as you get more and more in between. But if it can be represented by a fraction, it can be represented with a repeating decimal. And it works backwards too. You can make up any set of repeating digits, and it will be a rational number. 0.1 repeating is 1/9. 0.11 repeating is the same thing. 1/1 over 9/9, or 1/1 over 9/9. It's all 1/9. And of course, 2 times 0.1 repeating is 0.2 repeating, or 2/9. 0.3 repeating is 3/9, or a third. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Repeating is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 over 999999999. And of course, 0.9 repeating is 9 over 9. Even if a number repeats infinitely, it only has finite information. But when you don't repeat, there's just so many more possibilities. Any infinite sequence of numbers can make a real number. If it repeats, it's rational. If it doesn't repeat, the number is irrational. You could make a random irrational number between 3 and 4 by starting with 3 and rolling a 10-sided die an infinite number of times for the digits. What are your chances of getting exactly pi? What if you wanted to roll a rational number, ending in repeating digits like 3 plus a third? How long could you expect to keep rolling 3s on a fair die? Doesn't matter how lucky you are. If you literally roll infinite times, the chance of all 3s is 0. Exactly 0. You'll eventually roll something else. And then even if you go back to 3s for a while, you'll eventually roll something else again. Same with any rational. Imagine rolling a die and getting the same repeating sequence over and over again. How long would you expect that to last? Forever and ever through infinite rolls? Not a chance. Of course, the chance of getting all 3s is the same as getting any particular number. And if the chance of getting any particular number is exactly 0, then how can you get any number? It calls into question the very process of how to pick a random real number because you can't actually define a number through a series of infinite dice rolls. And math has a problem with randomness in general, and a single infinite random number would be infinite information, which doesn't fit in our universe. But before we get to transcendentals, let's talk algebraic. Algebraic numbers can by definition be defined by algebra, which, spoiler alert, not all numbers can. So for example, every rational number can be defined as some finite combination of digits and a division sign, a ratio, and throw in a minus sign sometimes. But you can also use other algebraic symbols to get irrational numbers. Some irrational numbers can be defined very simply with just a couple symbols, like square root 2. Or just a few, like phi, the so-called golden ratio, which is exactly 1 plus square root 5 over 2. Then some numbers can only be defined as part of an unsolved equation. Here, there's no algebraic way to solve for x. You can only approximate. But x is still defined. We don't care if we can solve for x as long as we can define it. No approximations. Which, by the way, it's totally crazy that you can make up algebraic equations that algebra can't solve, but also entirely inevitable, and a hint that there's much cooler math lurking behind algebra. And you can totally list a number of possible combinations of algebraic symbols, starting with combinations of 1 symbol, and then listing all valid combinations of 2 symbols, and then 3, and so on, up until an arbitrarily large, but finite, number of symbols. You'll have a lot of combinations that aren't valid, or that are equal to earlier ones, so they don't need to go on the list. But since you can list all possible algebraic combinations, The algebraic numbers match up 1-to-1 with the counting numbers. There's exactly as many. They have cardinality aleph null. This also matches up 1-to-1 with trying to list all numbers in decimal by putting together all combinations of digits, which is something a lot of people mentioned in response to Cantor's diagonal proof. Does this process get you all the numbers? Well, it gets you all possible finite combinations of digits, but nothing with infinite digits. No irrational numbers, and not most of the rationals either, since most rational numbers end in an infinitely repeating series. It's not a 1-to-1 number correspondence unless you can make a function that tells me exactly which unique entry on the list corresponds to pi, and which to 1/3, and which to Champernoun's constant. And the answer can't be, it gets to the irrationals at infinity, because first, that's not a whole number, and second, that's not 1-to-1, so yeah, probably not a 1-to-1 number correspondence. It's so simple to list all possible combinations of algebraic symbols, at least theoretically. But this list will never get to the numbers that would take an infinite amount of symbols to define, just as listing all combinations of digits will never get to numbers with infinite digits. These non-algebraic numbers are the transcendental numbers. They transcend algebra, and even if there is some infinite way to define them, with a pattern with a ... or with a summation, neither of which are algebra things, this list of all combinations doesn't get there. Maybe there's a non-algebraic way to approach a given transcendental number with a pattern that makes sense, like for pi and e. But for most numbers, we have no idea how to define them or whether they can be defined at all. I mean, we know there are more real numbers than there are ways to define a number. You can hit a random real number with a dart and we don't even know how to look at the result, how to differentiate it from all the other ones around it. Does the dart give results in decimal? Because no finite amount of digits will tell you what this number is. Does the dart report back in algebraic symbols? Because there's a 0% chance that you've hit a number that can be defined with a finite amount of algebraic symbols. Somehow, out of the uncountably infinite set of transcendental numbers, 100% of real numbers, most people only know pi and e, and maybe, like, Champernoun's constant. Maybe. And what else? What else is transcendental? Well, maybe one reason most people don't know more transcendental numbers is that nobody knows very many transcendental numbers. The field of mathematics is a little slow on figuring out how to prove whether numbers are transcendental or not. There's lots of open questions in transcendence theory, like, we don't even know whether Euler's constant is irrational or not, much less transcendental. Super embarrassing. Or maybe it's rational, or maybe tomorrow someone will come up with an algebraic equation for it, or maybe someone will prove that you can't prove whether or not you can prove it's transcendental. I mean, that kind of thing happens sometimes. Anyway, I think most people's problem with Cantor's diagonal proof is actually a problem with real numbers, with the idea that there are numbers that cannot be defined, that have an arbitrary combination of infinite digits, infinite information, because, yeah, that's pretty weird. Whoever decided to call them real numbers didn't think that one through. Thanks a lot, Descartes.